Hi everyone, welcome to part 2 for our video lecture on section 8.8 dealing with numerical integration. Now in the previous video we talked about how we can use Riemann sums to help us approximate the areas underneath the curve. Now this was a topic that you have seen in Calc 1, but now we're going to be talking about a different approach that's involving trapezoids, not rectangles. Now this approach, you might have also seen it in Calc 1, but it's oftentimes an optional topic. So I'm going to treat it here as if this is the first time that you're seeing it. Alright, so let's go ahead and begin here. Now since we are going to be using trapezoids to calculate the area underneath the curve, well, let's recall the area of a trapezoid. Well, if you're like me, you probably don't have the area of a trapezoid memorized because, well, we don't really encounter them all that much. So let's see if we can come up with the area of a trapezoid on our own. Alright, so let's consider this trapezoid here with a height h, then the length of one of the bases here, b2, and the length for the top, or if you can kind of call it the other base, b1. Alright, so you can treat this trapezoid as being basically made up of two geometric shapes. Alright, so here is my first geometric shape. I'm going to go ahead and create a rectangle. Now this rectangle here, notice that it's going to have a height h and a base of b1. So I'll call this one here a1 is equals to base times height, so b1 times h. Now I'm going to go ahead and create another rectangle right here. Now this other rectangle, notice that it's still going to have another height h. Now this one I'll call a2. Now a2 here is going to have a height of h. And now what is the base though? Well, the base, it's not b2, but instead this base is actually going to be b2 minus b1. Alright, so the thing is though, we're not really looking for area 2 though, but instead what we're looking for is area, well, this area right here, which happens to be 1/2 of a2. Now let me just call here a2, put it here on the outside, so a2, and we have a1 was equals to the height times b1, and a2 is equals to the height times the base, but the base was b2 minus b1. Alright, so the area of a trapezoid, I'll go here, area trapezoid is going to be the sum of the area for area 1, which is h times b1, plus 1/2 of the area of a2. But the area of a2 was h times b2 minus b1. Okay, now we can go ahead and simplify this. Now I'll simplify this by factoring out an h. So I'll put the h outside. I'll put the h, now I'll just keep everything in black. So we're going to have here h. Then what are we going to have? Well, we're going to have a b1 plus 1/2 b2 minus 1/2 b1. So this one here is going to give us then h times, well, we have now b1 minus 1/2 b1, so that's 1/2 b1 plus 1/2 b2. So this one is now going to give us, I'll factor out a 1/2, so it's going to give us a 1/2 h times b1 plus b2. And there we go. This is the area of a trapezoid. It's essentially the height times the average of the bases. And there we go. Alright, so this is the formula that we're going to be using. Now, I will point out though that typically the trapezoids that we're going to be encountering, they're not going to have this shape. They're instead going to be flipped on their sides. So we're going to have a shape like this. Now in this case, well, notice that the height is actually going to be given here by essentially kind of like the width of our previous rectangles. And in order to get the b1s and the b2s, well, the b1 here is going to be the function value evaluated at our left endpoint of the subinterval, which I'll call this one here f of x1 just for an example. And the b2 is going to be given by the height, but this time around it's going to be the height of the right endpoint of our subinterval, which I'll just call here x2. Okay, and the h in our typical example is going to be given by essentially the delta x. Alright, so putting this one here in terms of our function values and our width, or delta x, then the area of a trapezoid will be the same thing as 1/2 times delta x times f of x1 plus f of x2. Okay, so this is basically what we're going to be working with. Alrighty, so now I want you to take a look at the following graphs. On the left-hand side, we have here an approximation of the area underneath the curve using the midpoint formula. Now you get to see here that yes, there's going to be some parts where you're over-approximating, or overestimating, but there's also going to be some parts where you're underestimating it, and it's going to balance out. Now compare that one here to a trapezoidal approximation. We're going to have here our trapezoid, the first one. And notice here that, okay, well, it seems like it's giving us a better area than just the midpoint. And for the other trapezoid, it looks pretty nice. All right, so visually you can see here that, okay, well, it does seem like the trapezoidal rule is going to give us a much better approximation. All right, so what's going to be the formula? Well, the formula is not going to be any different than what we did with the Riemann sums. What we're going to be doing is adding the areas for each of our trapezoids. And here is the formula. So the formula is going to be given by, let me zoom in. There we go. The integral from a to b for f of x dx with a trapezoidal approximation is going to be approximately delta x divided by 2. This is what we have here. Delta x divided by 2 times the sum of the heights. But there is a particular thing to notice here. Notice that when we're adding the heights, we have a 2 right over here, but not at the beginning and not at the end. How come? So let's go back to our diagram here to see if we can go ahead and get some insight. All right, so if I wanted you guys to calculate the area of the first trapezoid, A1 here, well, A1 is going to be delta x divided by 2 times f of x naught plus f of x1. Now, if we add it to the area for our second trapezoid, put this one here, A2, well then we're going to have plus a delta x over 2 times f of x1 plus f of x2. Now, if we go ahead and simplify this, we can go ahead and factor out a delta x over 2. And what are we left with? Well, we're left with an f of x naught plus f of x1 plus f of x1 plus f of x2. Now notice here, well, it looks like you're adding the f of x1 twice. And you're adding it twice because, well, on the first trapezoid, it was the right endpoint. I'll put it here and I don't know, this color. All right, so on the first area, it was the right endpoint, but on the second area, it was the left endpoint. So if you were to continue on this pattern with more and more rectangles, yes, the middle ones would actually be counted twice, and that's why you have these 2's here. But notice that on the rightmost endpoint, since that's where you were stopping, there was no other left endpoint. So there we go. This is the trapezoidal rule. Okay, so let's go ahead and apply it in one problem here. Now, for this problem, I want to use 4 trapezoids of equal width to approximate the area of the region from our previous example. Whoops, this should have been example 1. Alrighty, so if we go ahead and begin with a sketch, we have the same shape as before, and as per usual, our delta x is going to be the same. It's going to be obtained by b minus a all over n, and based on the previous problem, we knew that this one here was 1/2 or 0.5. Now this one here is giving us our subintervals, so we're going to have a trapezoid with a width of 0.5, so there's going to be one trapezoid here, another trapezoid here, another trapezoid here, and there we go. Now we have our 4 trapezoids. I'm just going to go ahead and sketch them here. This is the first trapezoid. And you can already see here that, okay, yes, it seems like we're going to be getting a much better approximation for the area. Okay. All right, so what is this area? Well, we're going to have here, the formula is, remember, it's delta x divided by 2 times f of, well, in this time, for this problem, we were starting here at 1. So f of 1 plus 2 times f of 1.5. Put here 1.5. So 1, 1.5, 2, 2.5, and 3. All right, so plus 2 times f of 2 plus 2 times f of 2.5 plus f of 3. Now, one suggestion is that I do want to give you guys, so we have our delta x, right? Now the delta x was 1/2. So if we have a 1/2 divided by 1/2, I'm sorry, 1/2 divided by 2, well, remember that we can always multiply by the reciprocal of the denominator whenever we're dealing with a complex fraction. So if I multiply this one here by a 1/2, well, I can go ahead and multiply the top as well by 1/2. So really, we should be multiplying then by a, I'll put it here in blue, 1/2 times a 1/2. Now, the 1/2, this one was our width, and this one was coming from the formula. Okay, now what do we get when we add up all this function evaluations? Well, just as we did in the previous recording, we can use the calculator to our advantage, and I'm going to go ahead and plug all of this into the calculator to see what I get. All right, so I got approximately 5.3196, and once I multiply it by 1/4, let me just go ahead and put the approximations. So I got approximately 1.3299, which again, it's actually probably going to be really close to the actual value. Alrighty, now let's go ahead and take a look at another example, but this time around using a different function. So now let's see if we can go ahead and use the trapezoidal rule with n equals to 5 to approximate the integral from 0 to 1 of sine of x squared. And we want to round our final answer to 3 decimal places and compare this result with the result given by the calculator using the, well, the function, I forgot how to pronounce this, fn int. But yeah, it's just basically the approximation that the calculator can give us. Alrighty, so for this one here, I'm going to go ahead and begin with a sketch. Now this one here, you can go to our calculator to see how it looks like, but this is a sketch similar to what I got. Okay, alrighty, so let's go ahead and create our subintervals. Now we do want equal width, so our delta x is going to be equals to b minus a all over n. Now our b here is 1, our a is 0, divided by n, which is 5. So our delta x here is 1/5, which is about 0.2. Okay, so that means that each subinterval here is going to have a width of 0.2, so 0.2, 0.4, 0.6, 0.8, and 1. Alrighty, so creating the trapezoids. So this one here is going to be our first trapezoid. Then next one here. Okay, next trapezoid. So the 0.8 one here, there we go. And last but not least, there we go. Alrighty. Okay, so let's see. The area is going to be approximately, and again, we're going to have our delta x, so it's going to be a 1/5 divided by a 1/2. Sorry, well, divided by a 2, but again, as we just saw in the previous example, we just multiply it here by 1/2 times f of 0.2 plus 2 times f of 0.4 plus 2 times f of 0.6 plus 2 times f of 0.8 plus f of 1. And again, very, very important, don't forget, we do need to include these 2's here in our formula. Alright, so this one here will give us approximately, now I'm going to go ahead and put this into the calculator. So let's see what I'll get. I got approximately 0.314. And there we go. We're done with the problem. So as you can see here, guys, trapezoidal rule is typically much better than a Riemann sum. Okay, well, in the next video, we're going to be taking a look at an even better approach known as Simpson's rule. But yes, we'll see that here, or we'll see that in part 3 for our video lectures. See you there.